Dear students, in this video let us study about the transformers, principle, construction and working of transformer, the types of transformer, what are the energy losses that are occurring in a transformer. Now let us study about the transformers. What is a transformer? A transformer is a stationary device used to transform electrical power from one circuit to another without changing its frequency. What happens in a transformer? The applied alternating voltage is either increased or decreased with corresponding decrease or increase of current in the circuit. If a transformer converts an alternating current with low voltage into an alternating current with high voltage, then it is called a step-up transformer. This is one type of transformer. The other type of transformer is a step-down transformer, in which if the transformer converts an alternating current with high voltage into an alternating current with low voltage, then it is called a step-down transformer. Now we will study about the construction and working principle of a transformer. In the first case, let us study about the principle of a transformer. The principle of a transformer is the mutual induction between two coils. That is, when an electric current passing through a coil changes with time, an EMF is induced in the neighboring coil. And construction of a transformer. There are two coils of high mutual inductance wound over the same transformer core. The core is generally laminated and is made up of a good magnetic material like silicon steel. Coils are electrically insulated but magnetically linked via a transformer core, which is as shown in this figure 4.32. So this is a transformer in which there are primary winding of NP turns and secondary winding of NS turns. The current passing through the primary coil is IP, that is called primary current, and through the secondary coil it is IS, that is the secondary current. The voltage passing through the primary coil is primary voltage, and coming out of the secondary coil is called the secondary voltage, VS. And this is the transformer which we can see on the roads. So this is called a roadside transformer, which will give the voltage which is required for the households. The coil across which alternating voltage is supplied is called primary coil P, and the coil which from which the output power is drawn out is called secondary coil S. The assembled core and coils are kept in a container which is filled with suitable medium for better insulation and cooling purpose. Next we will see the working of a transformer. If the primary coil is connected to a source of alternating voltage, an alternating magnetic flux is set up in the laminated core. If there is no magnetic flux leakage, then the whole of the magnetic flux linked to the primary coil is also linked to the secondary coil. This means that the rate at which the magnetic flux changes through each turn is the same for both primary and secondary coils. As a result of flux change, EMF is induced in both the primary and secondary coils. The EMF induced in the primary coil or back EMF, EP, is given by this expression, EP equal minus NP d phi b by dt. But the voltage applied Vp across the primary is equal to the back EMF. So Vp is given by minus Np d phi b by dt. The frequency of alternating magnetic flux in the core is the same as the frequency of the applied voltage. Therefore, induced EMF in the secondary will also have the same frequency as that of the applied voltage. The EMF induced in the secondary coil E is given by Es equal minus Ns d phi b by dt, where Np and Ns are the number of turns in the primary and secondary coil respectively. And if the secondary circuit is open, then Es is equal to Vs, where Vs is the voltage across the secondary coil. So the expression can be written as Vs equal minus Ns d phi b by dt. So the ratio Vs to Vp, that is Vs by Vp equal to Ns by Np, that's equal to K. This K is called as voltage transformation ratio. And for an ideal transformer, the input power Vp-Ip is equal to output power Vs-Is. That is, Ip and Is, they are called the currents in the primary and secondary coil respectively. So these ratios Vs by Vp equal to Ns by Np equal to Ip by Is. And in other form, that is, in terms of amplitude of the corresponding quantities, this can be written as Vs by Vp equal to Ns by Np equal to Ip by Is, that's equal to K. Now let us consider two cases. In the first case, this number of turns in the secondary and primary coil. That is, if Ns is greater than Np, K is greater than 1. So Vs is also greater than Vp, but Is is less than I. So this is case of a step-up transformer in which the voltage is increased and the corresponding current is decreased. The second case, if the number of turns in the secondary coil is less than that in the primary coil NP, then K is less than 1. So Vs is also less than Vp, but Is, the secondary current, is greater than the primary current IP. This is the step-down transformer where the voltage is decreased and the current is increased. Next, we will see about the efficiency of a transformer. The efficiency E of a transformer is defined as the ratio of the useful output power to the input power. So eta equal to output power by input power into 100%, and the transformers which are highly efficient devices having their efficiency in the range of 96 to 99%, various energy losses in the transformers will not allow them to be 100% efficient. Now let us see what are the energy losses in a transformer. The transformers do not have any moving parts, so that its efficiency is much higher than that of rotating machines like generator and motors. But there are many factors which lead to energy loss in a transformer. Now let us study one by one. The first one being core loss or iron loss. This loss takes place in transformer core. The hysteresis loss, which we have already studied in the previous chapter, and the eddy current loss are known as core loss or iron loss. When the transformer core is magnetized and demagnetized repeatedly by the alternating voltage applied across primary coil, hysteresis takes place, due to which some energy is lost in the form of heat. This hysteresis loss is minimized by using steel of high silicon content in making transformer core. An alternating magnetic flux in the core induces eddy currents also in it. Therefore, there is energy loss due to the flow of eddy current called the eddy current loss, which is minimized by using very thin laminations of transformer core. Next, we will see about the copper loss. The transformer windings have electrical resistance and an electric current flows through them. Some amount of energy is dissipated due to Joule heating, and this energy loss is called copper loss, which is minimized by using wires of larger diameter. Next, we will study about the flux leakage. This happens when the magnetic lines of primary coil are not completely linked with secondary coil, and the energy loss due to this flux leakage is minimized by winding coils one over the other. Now let us see what are the advantages of alternating current that is used in long distance power transmission. Electric power is produced in a large scale at electric power stations with the help of AC generators. These power stations are classified based on the type of fuel used as thermal, hydroelectric, and nuclear power stations. Most of these stations are located at remote places. Hence, the electric power which is generated is transmitted over long distances through transmission lines to reach towns or cities where it is actually consumed. So this process is called as power transmission. But there is a difficulty during power transmission. A sizable fraction of electric power is lost due to Joule heating, that is given by A square R losses in the transmission lines, which are hundreds of kilometers long. These power loss can be tackled either by reducing current I or by reducing the resistance R of the transmission lines. The resistance R can be reduced with thick wires of copper or aluminum, but this increases the cost of correction of transmission lines and other related expenses. So this way of reducing power loss is not economically viable. Therefore, we can use a different method by using step-up transformer and step-down transformers. Let us see how. Since the power produced is alternating in nature, there is a way out. The most important property of alternating voltage that it can be stepped up and stepped down by using transformers could be exploited in reducing current and thereby reducing power losses to a greater extent. So at the transmitting point, the voltage is increased by the step-up transformer and the corresponding current is decreased by using this step-up transformer. And then it is transmitted through transmission lines as shown here. Then this reduced current at high voltage reaches the destination without any appreciable loss. And at the receiving point, the voltage is decreased and the current is increased to appropriate values by using step-down transformer as shown here. And then it will be given to the consumers. Thus, the power transmission is done efficiently and economically.